Hi, my name is Francisco Reales, and I'm going to talk about quantum resistant crypto systems for the subject of cryptography and security. So, first, I'm going to start with public key cryptography and especially the RSA algorithm to illustrate how quantum computers can help hack these systems. So, first, we start with a number that is composed of two primes, of the multiplication of two primes. And when we have this value n, we can find the Euler totem function as a multiplication of these two values p minus 1, q minus 1. And then we select a value of e that is coprime to this value that we obtain. Now, this value d that is going to be helpful to decrypt the message is going to be the inverse modulo phi. Is going to be calculated in this way, and so that we're going to have a value of the exponent for e and d. E is going to help us for the encryption, where the cipher text is going to be the message, the original message, to the power of the exponent e modulo n, and then the ciphertext is going to be sent through a channel where it's going to be decrypted as the ciphertext to the power of d modulo n. And this is the original message. Now, how secure is RSA? The problem here is that if we manage to factorize the value n as p and q as the two primes, then we could find, or an attacker could find, the value of phi, and then because e is public, they could calculate just like before the value of d, and they could decrypt the message. Now, the prime factoration is not an easy task to do, but it can be done. So let's see here. Let's assume that we have a value of n equals 77. And then if we have a value of g that is coprime to n, then we can say that Euler's theorem that this value 8 to the power of phi is going to be 1. And this is going to be helpful because then we can see that there is certain periodicity in the values of the modulo. So if we have 1 when r equals 10, for this value, is going to be repeated over time for different values, and that's the period of the signal. Now, let's assume that we already know this value because we have this sequence. If we have that g to the power of r equals 1 from this, or yeah, it is 1 modulo n. Now we can say that g to the power of r minus 1 modulo n equals 0, which means that it is a factor of n. Now we can rewrite g to the power of r minus 1 as this multiplication. And because we already know the value of r, which is 10 for this case, we just have to rewrite the multiplication, and then we would have these values. Now, these values are too big, so we could use Euclides' algorithm to find the maximum common divisor, which would give us p equals 7 and q equals 11. And that would be the prime factoration. Now, this is something, this was a very easy example, but if the number is large, we can use another tool called the Fourier transform, which it's able to find the periodicity in signals, because here we have a signals with a given period. What the Fourier transform does is for a given signal that has certain periodicity, see it as a superposition of sine waves, of sine signals, and then it would allow us to get the period of the signal. Now, these calculations can also be done by a quantum computer, because one qubit um, basically has a superposition of two states, which is 0 and 1. Um, so the superposition is just the sum, where the sum of both states will be 1, because this is a probability. And if we start adding more qubits, then it would add to the superposition. So if we manage to, instead of an state that is 0 or 1, we manage to change the states as if they were signals, then we will have the superposition of all the signals, with the difference that the sum of everything will be 1, because it's still a probability. So having different qubits could help us calculate this Fourier transformation. So the Fourier transform um, would then allow us to have this period, and then we could have the factorization of this large number. Now we have different type of quantum resistance systems depending on the working principles. So we could have code-based cryptography, lattice-based cryptography, hash-based cryptography, and even more. So let's see in depth the lattice-based cryptography, to give an example of how it works. So let's first assume that we have some vectors that form the basis of the lattice, which means that there are vectors which a linear combination form the whole lattice. So we could have some vectors that are short and that are nearly orthogonal vectors, which are, say, the easy ones. Because as we can see here, if we manage to encode um, a message as a vector in the lattice, and that's what we have here, going there to that message as a linear combination of these two vectors would be very easy. While if we have some long um, highly non-orthogonal vectors, just like that, just like these two vectors that we have here, going to that message is going to be harder. Now, this is what we'll use as public key encoding, while the easy is the private key. So that is going to be harder for someone that gets these two vectors to find the correct linear combination of vectors that would achieve the message. So the let's talk a little bit about the vulnerabilities, and there is a hardness assumption that, as I was saying here, if we have these two vectors, then finding the message is hard. Now, if we if we in the future find an efficient algorithm to find or to solve this problem, then this would be a vulnerability for the system. Also, it depends on the dimension. This is only two dimensions to illustrate the problem. However, it could go to 1000 dimensions, which would make the problem harder to solve. So it would make it a stronger crypto system. For further research and future work, um, it's going to be discussed some papers that implement um, through this type of crypto systems, try to solve different vulnerabilities that they have. That's what is going to be analyzed in the research paper, and these are gonna be different. These are the ones that has been researched so far. However, there will be more for the actual research paper.